For topic 3, we're going to talk about something called conditional probability, and it is easy to confuse the idea of conditional probability with the probability of events involving and, where you have dependent events, okay? But conditional probability is a whole different critter, okay? So first of all, for a definition, it says the probability of event B, assuming that A has already occurred, is the conditional probability of B given A, denoted by the probability of B, and then you do like a slash A, okay? Now, what's different about this is while in dependent events, like what we talked about in the previous video, the probability of one will impact the probability of the second in the sense that it can alter the sample space slightly, okay? So like when we're talking about donuts, you grab a donut, you eat it, there's no longer the same number of donuts in the box, okay? What's different here about conditional probability is you have one event that completely alters the sample space for the second event, okay? So we think of conditional probability as the probability that an event occurs if the sample space is restricted by another event. Okay, so we have this like massive sample space restriction. Okay, and one thing you can always do, at least in my world, I will always do it this way. I will always write conditional probability in such a way that there is a given that statement. What is the probability of blah given that blah has already happened? So look for that given that statement, okay? So let's go ahead and just dive in. I think this will make a bit more sense once you see it kind of in practice, okay? So for example 3, it says find each probability. And for part A, it says a letter is randomly selected from the letters of the English alphabet. Find the probability of selecting a letter that precedes H, given that the outcome is a vowel. Okay, so we want to look for that given that statement. This right here restricts our sample space. This is the sample space restriction. So let's go ahead and just write out the alphabet. We have A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, W, X, Y, Z. Okay, so we have the alphabet here, and we're looking for the probability that we select a letter that precedes H, so a letter that comes before H, given that the outcome is a vowel. Okay, so that means we can only consider vowels. Okay, we have completely restricted our sample space to vowels. Okay, so let's write this out. We want the probability of something that precedes H, given that we're looking at the vowels. So this becomes, again, our sample space. So when we're looking at just the regular old alphabet, how many vowels do we have? Well, we have A, E, I, O, and U. So at this point in time, my denominator can only be the vowels, so my denominator is 5. Of those 5 vowels, how many precede H? Well, H is right here, okay? So how many of the vowels are before H? Well, 2 of them. So the probability in this case, so the probability of choosing a letter that precedes H, given that the letter is a vowel, would be 2/5. Okay, and that's it. Okay, that is conditional probability. So again, you have the probability of one event, assuming the sample space is completely restricted by a second event. Okay, so let's look at part B. It says there's another typo here. I should have, so if you have the printed set of notes, there is a typo. This should say that we are choosing, we have tiles numbered 1 through 30. That is deepest apologies on my part. Okay. So it says you have tiles in a bag numbered 1 through 30. A tile is randomly selected from the bag. Find the probability of selecting a number greater than 15, given that the number is even. So what we're looking for is the probability of picking something greater than 15, given that the number is even. Okay, so let's go ahead and just list out all of the evens because this right here is our sample space. The given that statement is what restricts our sample space, okay? So given that the number is even is our restriction, so we can go, we're 1 through 30, remember? So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. Okay, so we've got these numbered tiles 1 through 30. We know we have restricted our sample space to just the even numbers. Okay, so of these even numbers, how many would be bigger than 15? Well, 15 would be right here between 14 and 16. Okay, so looking at all of the even numbers, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 of them. And of those 15 even numbers, how many are bigger than 15? Well, 1, starting here and going this way, we have 1, 2, 3, 4, 5, 6, 7, 8. So the probability of choosing a number greater than 15, given that the number is even, would be 8/15. So again, that given that statement completely restricts your sample space. And then from that new sample space, what would the probability be of that first event that's listed? Okay, let's look at a couple more. Okay, part C, it says you are dealt one card from a 52 card deck. Find the probability of getting a black card given that the card is a king. Okay, so we want the probability of drawing a black card given that the card is a king. So this right here is our sample space. Remember, the given that statement restricts our sample space. So in a deck of cards, how many kings are there? Well, there's a king of hearts, a king of diamonds, a king of clubs, and a king of spades. So there's 4 hearts. Of those, or 4 hearts, good Lord, 4 kings. Of those 4 kings, how many also happen to be black? Well, the king of spades and the king of clubs. So 2/4 or 1/2 of the cards would be black, given that the cards are kings. So again, the given that statement restricts your sample space. Okay? Last one for this example, it says you are dealt one card from a standard 52 card deck. Find the probability of getting a red card given that the card is a face card. So remember, face cards are jack, kings, and queens. Okay, so we want the probability of drawing a card that is red given that we're limited to face cards. So remember, this is our sample space right here. So first of all, how many face cards are in a deck? Well, there are 3 face cards, a jack, a queen, and a king for each of the 4 suits. So there's basically 3 face cards for the hearts, 3 face cards for the diamonds, 3 face cards for the clubs, and then 3 face cards for the spades. So that would give me 12 face cards. Of those 12 face cards, how many are red? Well, we've got a king, queen, and jack of diamonds, a king, queen, and jack of hearts. So that would give me 6 red cards out of the 12 face cards, or the probability would just be 1/2. Okay, so remember, when you're dealing with conditional probability, you are completely restricting your sample space to something that's stated very clearly. The given that statement is your sample space restriction. Okay, example 4, we're going to look at some empirical probability problems. So remember, empirical probability is what has been observed to have happened versus theoretical, which is what like should happen if events are equally likely. So here we have a table that shows the outcome of car accidents in Florida. I'm assuming at some point in time this was real world data. I don't have like the actual information on when this was, but let's assume at some point in the past this was real world data. And as morbid as this is, this table splits things into whether the driver survived or died, and then whether the seatbelt was worn or not worn. So we have a totals row, a totals column. The total that we're looking at would be this 577,006. But remember, when we're dealing with conditional probabilities, we are restricting our sample space. So we're not going to get too hung up on that 577,006 because it may not impact either of these problems. Okay, so this should say, let's see, find each probability outlined below. For part A, it says, find the probability of surviving the accident given that the driver wore a seatbelt. Okay, so we want the probability that the driver survived given that they did wear a seatbelt. So this is our sample space restriction. So that means we can only look at this column where the driver wore the seatbelt. Okay, so we want to look at the number of people that wore a seatbelt, which was 412,878. Okay. And of those 412,878 people, how many survived? Well, 412, 368. And I didn't specify here, but a lot of times when you're dealing with tables of values, like when you're dealing with the empirical probability, a lot of times we'll write these as decimals. I didn't specify here, but let's go ahead and do decimals to 2 decimal places here. So round to the hundredths place. All right, so we can do this on our God, I can't speak today, our own handheld calculators. So we have 412, 368 divided by 412, 878. I'm going to go, well, let's go 3 decimals because this one's not going to work out nicely if we go 2 decimals. So let's go round to the thousandths place, so 3 decimal places. All right, so on the calculator, you should get 0.99876476683. So I'm going to go 0.999. So you are much more likely to survive the car accident, assuming you wear your seatbelt. Okay. Now for part B, it says find the probability of not wearing the seatbelt, given that the driver did not survive the accident. So again, you're choosing somebody randomly from this table. What is the probability that they were not wearing the seatbelt, given that they did not survive? So we have the probability of no seatbelt given died. Okay. Now, those that passed away, that is our sample space restriction. We can only consider those that did not survive the car accident. So this is our sample space. And you can see we have the given that statement here, given that a driver did not survive the accident. So we can only consider this row right here where the driver did not survive. Okay, so the total here is 2,111. And of those 2,111, how many did not have a seatbelt on? And that would be 1,601. And again, I'm just going to go to my calculator here, the handheld, since this one's pretty easy. So 1601 divided by 2111. And we get point, if we go 3 decimal places, you should get 0.758. Okay, so you could certainly do conditional probability with a table of values, but read the questions very, very carefully. I could say, hey, if we selected one person at random, what is the probability that the person wore a seatbelt and died? Okay, that's kind of different. That would be looking at just this number right here over this number right here. But if I say, what is the probability of selecting a person that wore the seatbelt? Given that the person died, that means we can only consider those that passed away in the car accident. Okay, so the reading here, the wording of these problems is going to be really, really subtle. So for me, I promise if I am wanting you to do conditional probability, I will very clearly put a given that statement. Okay. So when you see given that, your brain should automatically think conditional probability, we're completely restricting the sample space. Okay. So that is it for 11.7, and we are rapidly wrapping up chapter 11. We have one more section to go, and it is on something called expected value.